Intrinsic and extrinsic semiconductors. Semiconductors are classified into two types, namely intrinsic semiconductor, extrinsic semiconductor. Intrinsic semiconductor. A semiconductor in a very pure form is called an intrinsic semiconductor. Germanium and silicon are intrinsic semiconductors. The crystalline structure and energy band diagram of germanium are shown here. At absolute zero, all electrons of the semiconductor are tightly held. The inner electrons are bound, whereas the valence electrons are engaged in covalent bonding. At this temperature, covalent bonding is very strong and hence there are no free electrons. Therefore, the semiconductor crystal behaves as a perfect insulator at absolute zero. At room temperature, the valence electrons absorb thermal energy and get excited. Due to absorption of energy, the valence electrons jump from the valence band to the conduction band. Whenever a valence electron drifts from valence band to conduction band, a vacancy is created in the valence band, and such a vacancy is called a hole. Thus, an electron-hole pair is produced. Now, if a potential difference is applied across the semiconductor, current would flow through the external circuit. This type of semiconductor where the conductivity is due to the movement of electrons and holes is called the intrinsic semiconductor. Extrinsic semiconductor. Conductivity of intrinsic semiconductors is very less at room temperature. To increase the conductivity, a small amount of external impurity is added to the pure semiconductor. Such a semiconductor then becomes an impure or extrinsic semiconductor. The process of deliberate addition of a very small amount of impurity into an intrinsic semiconductor to increase its conductivity is called doping, and the impurities are called dopants. The impurities are classified as donor impurities and acceptor impurities. Donor impurities are those elements which donate excess of electrons for conduction. Pentavalent elements like antimony, phosphorus and arsenic are donor impurities. Acceptor impurities are those elements which create positive carriers or holes that can accept electrons. Trivalent elements like boron, gallium or indium are acceptor impurities. Acceptor impurities are also known as p-type impurities. Depending upon the type of impurity added, the extrinsic semiconductors can be classified as n-type semiconductor and p-type semiconductor. Doping a germanium crystal. Displayed here is the crystal structure of germanium. If to a pure germanium crystal, a small amount of pentavalent impurity like arsenic is added, then 4 of the 5 valence electrons form a covalent bond with the 4 valence electrons of germanium, and the 5th one will be available for conduction. These types of semiconductors, where electrons are the current carriers, are known as n-type semiconductors. When a trivalent impurity like boron, gallium, or indium is added to a pure germanium crystal, only 3 covalent bonds are formed, and there exists a vacancy in the 4th bond, creating a hole as shown in the figure. These types of semiconductors, where positively charged holes are the current carriers, are known as p-type semiconductors.